At the edge of the known universe lies a silence so complete that even light cannot escape it. Here, gravity is not merely a force, but a devouring abyss, bending time and space into a single, inescapable fold. Photons stretch into infinity, their final cries frozen at the threshold of an invisible wall. It is called the event horizon, a boundary without surface, a shadow without substance, the ultimate frontier of reality. For decades, it has been imagined as the dominion of the black hole, a place where matter collapses without end, a singularity of infinite density, hidden forever behind a curtain that no eye can pierce. Yet, in the whispers of theoretical physics, another vision emerges, stranger, subtler, and perhaps more merciful. The Gravastar, not a monster of collapse, but a phantom of balance, where quantum vacuum energy holds back the final plunge into nothingness. Beyond this veil, humanity confronts its most haunting question: what does nature allow in its deepest silence? Is the cosmos built to accept infinities, or does it hide a gentler truth, cloaked in the disguise of black holes? The event horizon is more than a boundary of physics. It is a mirror to human wonder, a place where science meets philosophy, where fear dissolves into awe. To cross it is impossible. To imagine what lies beyond is irresistible. Between black hole and Gravastar lies a mystery that challenges not only equations, but existence itself. The story of black holes did not begin in the computer age, nor in the silent domes of radio observatories. It began centuries earlier, in an era when the universe was still illuminated by candlelight and curiosity. In 1783, the English natural philosopher John Michell sat with pen and paper, contemplating the mysteries of gravity. He imagined a star so massive, so dense, that its pull would be inescapable even for light itself. If such a star existed, he reasoned, it would be invisible, hidden not by distance, but by its very nature. He called it a dark star. It was a thought experiment, nothing more. Yet within those quiet lines of ink lay the seed of a concept that would one day haunt the imagination of modern physics. Decades later, Pierre-Simon Laplace in France echoed Michel's speculation. In his Exposition du Système du Monde, he suggested that if a star's mass exceeded a certain threshold, not even the swiftest ray of light could flee from its surface. To the philosophers of the Enlightenment, such an idea was thrilling, but it remained abstract. Newtonian physics, powerful though it was, could not predict such extremes with certainty. For a time, the dark star faded into the background of science, a ghostly curiosity too exotic to be pursued further. It would take the 20th century and the radical genius of Albert Einstein to resurrect the vision in a form far stranger and far more terrifying. In 1915, Einstein unveiled the general theory of relativity. Space and time were no longer static, empty backdrops for the drama of matter and motion. They were active, dynamic fabrics, curving and warping under the influence of gravity. This was a cosmos where geometry itself could be bent, where time could slow, where light could be trapped. Barely a year later, on the frozen battlefields of World War I, a German physicist named Karl Schwarzschild wrote a letter to Einstein. Working from the front lines, under skies lit by artillery rather than starlight, Schwarzschild had solved the equations of general relativity for the simplest possible case: a perfectly spherical mass. His solution revealed something extraordinary: a radius beyond which space-time folded in on itself. Any object compressed within this boundary would become invisible to the rest of the universe. Today, we call this threshold the Schwarzschild radius. It was the first mathematical description of what would eventually be called a black hole. Period. Einstein was intrigued, but skeptical. To him, the mathematics was undeniable, but the physical reality seemed absurd. He believed nature had ways of preventing such extremes. Many physicists agreed. Singularities, points of infinite density, felt like a breakdown of knowledge rather than a prediction of nature. Surely, the cosmos was not so unkind as to harbor infinities in its heart. And so, for decades, the idea of black holes remained suspended between mathematics and disbelief. They existed on paper, but not in the sky. Even the name black hole would not appear until the 1960s. Yet slowly, evidence began to gather that the universe did not share human skepticism. By the mid-20th century, astronomers peering through increasingly sophisticated telescopes noticed stars behaving strangely. Some orbited unseen companions that emitted no visible light, yet exerted immense gravitational influence. In the 1960s, the newly launched X-ray satellites detected violent emissions from binary star systems. One of these, Cygnus X1, revealed a hidden partner, a collapsed object too massive to be a neutron star, too invisible to be anything but the long-feared black hole. For the first time, Michel's dream and Einstein's equations stepped out of theory and into observation. This was only the beginning. Radio telescopes mapped quasars, the blazing cores of distant galaxies, and revealed that at their hearts lay monsters millions, even billions of times the mass of the Sun. These were not curiosities on the edge of physics. They were central to the architecture of the cosmos. Every major galaxy seemed to host a supermassive black hole at its center, including our own Milky Way. What began as a forgotten speculation in the 18th century was suddenly the scaffolding of the universe itself. The discovery phase of black holes, then, was not a single moment, but a slow unveiling. From Michel's ink-stained desk, to Laplace's musings, to Einstein's equations, to Schwarzschild's wartime calculations, and finally to the satellites and observatories of the space age. Each step carried humanity deeper into the realization that the cosmos was stranger than intuition allowed. The dark stars were not myths. They were real, and they were everywhere. Yet even as evidence solidified, unease remained. If black holes were real, then so too were their singularities, places where the laws of physics collapsed. It was a truth as exhilarating as it was terrifying. And so, alongside the rise of black hole astronomy, came a parallel search for alternatives, for ways the universe might protect itself from infinities. Among these whispers of resistance, a new idea would eventually emerge: the Gravastar, a cosmic phantom hiding in the shadow of black holes. But before that debate could unfold, the scientific world had to confront the shocking reality that black holes themselves were no longer imagination. They were part of the universe's deepest design. By the late 20th century, the evidence had become overwhelming. Black holes were no longer distant curiosities. They were the silent architects of galactic evolution. In the heart of the Milky Way, radio telescopes trace the orbits of stars whipping around an unseen mass. Year after year, astronomers measured their trajectories with growing precision. By the 1990s, the results were undeniable. At the very center of our galaxy lurked an object 4 million times the mass of the Sun, packed into a space no larger than our solar system. Sagittarius A star had revealed itself, not through light, but through the invisible gravity binding the stars around it. The discovery was profound. Our galaxy was not unique. From Andromeda to the faintest smudges of light on the cosmic horizon, nearly every galaxy studied carried a similar secret: supermassive black holes were not exceptions. They were universal. Some dwarfed even imagination, with masses billions of times greater than the Sun. Their existence raised questions that science was barely equipped to ask. How did such giants form? Were they born in the early chaos of the universe, or did they grow slowly, consuming stars and gas across eons? The discovery phase was now not only about identifying black holes, but about understanding their place in cosmic history. At the same time, black holes revealed themselves in violent detail through quasars and active galactic nuclei. These distant beacons shone brighter than entire galaxies, fueled by matter spiraling into black holes at their centers. As particles accelerated near the event horizon, they emitted torrents of energy, flooding the cosmos with radio waves, X-rays, and gamma rays. What had once been imagined as silent, lightless prisons were now seen as engines of unimaginable power, shaping the growth of galaxies and possibly influencing the distribution of matter in the universe itself. Yet with every new observation, tension grew. The mathematics of relativity predicted singularities, points of infinite density where the known laws of physics disintegrated. But infinities are not physical. They are signs that theory has reached its breaking point. For many physicists, the reality of black holes was both a triumph and a tragedy. A triumph of discovery, but a tragedy for knowledge, because within their depths, equations ceased to function. It was here that doubt once again began to creep into science. Could the universe truly host infinities? Or were black holes, as Einstein once suspected, illusions created by imperfect understanding? Some began to wonder if another solution might exist, an alternative that explained the observations but avoided the catastrophic collapse to a singularity. The seed of this doubt grew stronger with new paradoxes. In the 1970s, Stephen Hawking showed that black holes were not entirely black. Through quantum effects at the event horizon, they could emit radiation, now known as Hawking radiation. This revelation deepened the mystery because it suggested black holes could eventually evaporate. But if they vanished, what happened to the information carried by everything that had fallen in? According to quantum mechanics, information cannot be destroyed. Yet according to relativity, black holes erased it. The contradiction struck at the foundations of physics. By the dawn of the 21st century, black holes stood as both the most confirmed objects in astronomy and the most unsettling riddles in science. The Event Horizon Telescope, a global network of radio observatories, is prepared to capture the first direct image of a black hole's shadow. Gravitational wave detectors like LIGO and Virgo began recording the ripples of spacetime caused by the collisions of massive black holes. Humanity was not only detecting their presence, it was listening to their depths. And still, the mystery remained incomplete. The discoveries revealed black holes with astonishing clarity, yet their interiors remained sealed behind the event horizon. No telescope could see within. No signal could escape. To study them was to forever circle a boundary that refused to be crossed. This was the paradox of discovery. The closer science came to black holes, the further away their true nature seemed to drift. Out of this paradox rose the quiet suggestion of an alternative. If black holes were too catastrophic to be real, perhaps something else existed in their place. Something that could mimic their gravitational pull, their horizons, even their violent radiation, but without the singularity. In 2001, physicists Paul Mazur and Emil Matola introduced a radical possibility: the Gravastar, or gravitational vacuum star. Unlike black holes, Gravastars contained no point of infinite density. Instead, they were thought to consist of a thin, ultra-dense shell surrounding a core of dark energy-like vacuum. From the outside, a gravastar would appear indistinguishable from a black hole. But inside, it would be an entirely different beast. This idea did not yet dominate, but it marked the first true challenge to the supremacy of black holes. Suddenly, the story of discovery had a fork in its path. Observations proved that something extraordinary lurked in the centers of galaxies and in the depths of massive stars. But whether those objects were the singularities of Einstein's nightmares or the hollow shells of Mazur and Mottola's imagination remained unclear. The discovery phase, then, was not merely a triumph of evidence. It was a mirror held up to science itself. Humanity had uncovered objects that matched equations written on paper centuries before. Yet those very objects now threatened to unravel the consistency of physics. Were they black holes, devourers of light and keepers of infinities, or gravastars, quiet phantoms preserving the universe from collapse? The only certainty was this: the cosmos was stranger than humanity had dreamed, and discovery was only the first step into a much darker mystery. The moment black holes shifted from speculation to evidence, science itself trembled. Here was an object so alien that it tore through the very framework of physics. Stars had been cataloged, galaxies measured, cosmic distances calculated, but the black hole stood as a contradiction in motion, a place where the laws that described the universe simply broke down. At its heart lay the singularity. General relativity described it as a point of infinite density and zero volume, a place where all the mass of a collapsed star was crushed into nothingness. The equations of Einstein did not offer a way around this. They predicted it with ruthless consistency. Yet, infinities were not supposed to exist in nature. They were signs of failure, mathematical warnings that theory had reached the edge of its power. For physicists, this was both exhilarating and terrifying. If singularities were real, then the cosmos itself contained places where knowledge ended. This shock was amplified by the strangeness of the event horizon. The horizon was not a surface, not a shell of matter, but a boundary carved into space-time itself. For an outside observer, time appeared to slow as an object approached the horizon. Its light stretched into infinite redness until it froze forever on the brink. But for the falling traveler, hypothetical they might be, time would flow normally, carrying them across the horizon in an instant. Two realities, two perspectives, both true and both irreconcilable. The horizon revealed relativity's strangest gift, that reality depended on where one stood. Then came Hawking's revelation. In the 1970s, applying quantum field theory to the curved spacetime around a black hole, Stephen Hawking discovered that horizons were not silent. Quantum fluctuations near the boundary could create pairs of particles, with one falling in and the other escaping. The escaping particle would appear as radiation, a slow leak of energy from the black hole. Over time, this Hawking radiation would cause black holes to shrink and eventually vanish. It was a discovery that changed everything, for it suggested that black holes were not eternal prisons. They could evaporate. And yet, the implications deepened the shock. If black holes could evaporate, what happened to the information locked inside them? The details of every star, every atom, every photon that had ever fallen across the horizon, did they vanish as well? According to relativity, yes. According to quantum mechanics, no. This was the birth of the information paradox, perhaps the most profound contradiction in modern physics. The paradox unsettled more than theory. It unsettled philosophy. For centuries, physics had been built on determinism, the belief that the universe was governed by laws precise enough to predict its every motion. If black holes destroyed information, then determinism was broken. The future could no longer be perfectly connected to the past. Reality itself would be incomplete. Observations only deepened the strangeness. Quasars roared across cosmic distances, powered by matter spiraling into invisible abysses. Gravitational waves rippled across spacetime from collisions of unseen titans. Everywhere they looked, astronomers found black holes not as exceptions, but as essential players in the cosmic story. They were not rare monsters. They were the engines of galaxies, the keepers of structure, the sculptors of matter. The shock was not merely that black holes existed. It was that the universe was built upon them. And if they contained infinities, paradoxes, and contradictions, then the very foundation of science was resting on a fault line. The scientific world had discovered not just objects, but questions too large for its own language. And in that silence, a haunting thought arose. Perhaps what we called black holes were not what we believed. Perhaps, hidden behind the veil of the horizon, the universe concealed something else. Something stranger than a singularity, and perhaps more merciful than an abyss. The deeper the study of black holes became, the sharper the contradictions grew. For physicists, each discovery felt like a triumph and a defeat all at once. Evidence confirmed their reality, but also exposed the edges of human understanding. Black holes were not simply objects. They were cracks in the map of knowledge, portals where the known laws of science began to collapse under their own weight. The singularity stood as the most immediate horror. To imagine all the matter of a star crushed into infinite density was to accept that nature permitted an end to physics. At the singularity, relativity's equations no longer produced meaningful results. Space curved infinitely, time collapsed into nothingness, and cause and effect lost all coherence. If singularities were real, then the universe contained regions where prediction, explanation, and reason ceased to exist. For centuries, science had been the pursuit of order. Black holes suggested a core of chaos at the very heart of existence. This chaos was made worse by the paradoxes of the horizon itself. To an external observer, matter falling toward a black hole never truly crossed the horizon. It slowed, reddened, and faded, suspended forever on the edge of visibility. But to the falling matter, the journey was swift, carrying it past the horizon in an instant. Two observers, two truths. Relativity declared both perspectives valid, and yet they were irreconcilable. Reality itself seemed to fracture at the rim of the abyss. Hawking's work only widened the fracture. Hawking radiation was not a gentle correction. It was a revolution. It meant black holes could eventually disappear, leaving behind no trace of the information they had swallowed. But the laws of quantum mechanics declared that information was indestructible. Something as simple as the arrangement of atoms in a burned book was preserved in the smoke and ash. But in a black hole, even that final trace was lost. The result was an impossible contradiction. Two great pillars of modern physics, relativity and quantum mechanics, stood in direct conflict. The shock was not confined to equations. It seeped into the philosophy of science itself. Determinism, the idea that the past and future were unbroken by gaps of knowledge, was suddenly called into question. If black holes destroyed information, then the chain of cause and effect was broken forever. The universe would no longer be a clockwork cosmos, but a place where histories could vanish without a trace. As the 20th century drew to a close, experiments added weight to the paradox. The discovery of gravitational waves by LIGO in 2015 revealed the sound of black holes colliding, ripples in spacetime itself. These detections confirmed Einstein's predictions, but also underscored the violent reality of horizons and singularities. The universe rang with the music of contradictions, each collision reinforcing the presence of objects that theory could not fully describe. Astronomers, too, struggled with the images captured by the Event Horizon Telescope. The silhouette of M87 star, revealed in 2019, was a triumph of technology. It showed the dark outline predicted by relativity, the shadow of a horizon. But the image also posed the unspoken question: what exactly cast that shadow? Was it truly the maw of a singularity? Or could it be the edge of something stranger? A gravastar, a hollow phantom disguised as a black hole. The scientific shock of black holes was thus twofold. First, they forced humanity to accept their reality, confirmed by observation beyond all doubt. Second, they demanded explanations that science did not yet have. Relativity could describe their exterior, but not their core. Quantum mechanics could predict behavior near horizons, but not reconcile the loss of information. Each step forward only sharpened the contradictions. The paradoxes multiplied. The firewall hypothesis, which suggested a wall of energy at the horizon. The fuzzball model from string theory, where horizons were replaced by tangled strings. The holographic principle, which proposed that the information of a black hole might be encoded on its boundary rather than lost inside. Each attempt to resolve the contradictions revealed how desperate science had become to escape infinities. And yet, the shock was not despair. It was also an inspiration. Black holes became laboratories for ideas that might one day unite relativity and quantum mechanics. Two frameworks still divided. They became the crucibles of unification, where the deepest mysteries of spacetime could be tested. Their paradoxes were not walls, but doors. The discovery of black holes had shocked the scientific world, but the true test of their nature lay in deeper investigation. Observations had revealed their shadows, their influence on stars, and the violent light emitted by matter spiraling into their grip. Each new advance demanded more precision, more evidence, more daring attempts to probe the veil of the event horizon. If discovery had brought awe, investigation brought an unrelenting hunger to know, and with it, a confrontation with mysteries even stranger than first imagined. In the mid-20th century, astronomers began to realize that black holes were not isolated curiosities, but central engines in the cosmos. Quasars, once mysterious points of blinding brightness at the edges of the visible universe, revealed themselves as galaxies lit by matter falling into supermassive black holes. These objects consume stars and gas with such violence that they emitted more energy than trillions of suns. Quasars were not merely signals of black holes. They were the brightest beacons in existence, their light traveling across billions of years to reach Earth. The deeper astronomers looked, the clearer it became that black holes were woven into cosmic evolution. Galaxies were not random collections of stars. They were shaped and stabilized by the black holes at their cores. Observations of stellar orbits near Sagittarius A star, the supermassive black hole in the heart of the Milky Way, showed stars moving at extraordinary speeds around an invisible anchor. Night after night, year after year, astronomers traced their motion, And every orbit confirmed the same conclusion. Something immense and invisible dominated the galactic center. But to understand these giants, science needed new tools. Telescopes were no longer enough. Instruments had to expand into the invisible. Radio, X-ray, and gamma ray. The Chandra X-ray Observatory revealed gas heated to millions of degrees in the throes of black holes. Radio telescopes captured jets of plasma streaming across light years, accelerated by magnetic fields twisting around event horizons. The electromagnetic spectrum became a map of violence, each wavelength revealing a different aspect of the abyss. The 21st century brought the boldest leap. The Event Horizon Telescope, a network of observatories spread across the globe, linked together through a technique called very long baseline interferometry, turned Earth into a single giant eye. In 2019, after years of anticipation, it delivered the first direct image of a black hole's shadow, M87, a behemoth 6.5 billion times the mass of the Sun. The image was blurred, faint, imperfect, but it was historic. For the first time, humanity had seen the silhouette predicted by relativity itself, a glowing ring of matter surrounding a darkness that could not be crossed. Yet deeper investigation brought not certainty, but questions. Was the shadow truly the sign of a singularity? Or could a Gravastar produce the same effect? The data matched relativity with astonishing precision, but the possibility of alternatives lingered. The difference between a black hole and a Gravastar might not lie in what telescopes could see, but in what they could never reach, the space beyond the horizon. Meanwhile, gravitational waves offered a new way to listen to black holes. In 2015, the LIGO Observatory detected ripples in spacetime from the merger of two black holes over 1 billion light-years away. The signal matched predictions perfectly, confirming that massive, invisible objects were colliding in the darkness. Each new detection added detail: the masses of the black holes, their spins, their distances. Virgo in Italy joined the effort, and the universe revealed itself in vibrations rather than light. Black holes, once silent, now had a voice. But the deeper the data grew, the more it challenged science. Simulations showed that Gravastars too might merge, producing gravitational waves almost indistinguishable from those of black holes. Subtle echoes, tiny variations in the signals, might betray their presence. But the instruments were not yet sensitive enough to confirm or deny. The abyss continued to whisper in riddles, leaving physicists uncertain whether they were listening to singularities or shadows of something else. This was the nature of deeper investigation. The closer humanity came to the truth, the more elusive it became. Black holes, or Gravastars, or something stranger still, each observation confirmed their reality, but none pierced their essence. Science had reached the threshold of the horizon, but the interior remained sealed. The quest for understanding pressed on. Satellites, supercomputers, and collaborations of thousands of scientists poured into the mystery. The event horizon had become not just a boundary in space, but the frontier of human thought. Beyond it lay not only the fate of stars, but the fate of knowledge itself. As instruments sharpened and data deepened, black holes revealed themselves not only as astronomical curiosities, but as testing grounds for the deepest questions in physics. To peer into their nature was to confront the very structure of reality itself. Every new observation carried with it the promise of clarity, and yet every discovery only added new shadows to the mystery. One of the most critical avenues of deeper investigation came from studying the environments surrounding black holes. Gas clouds, spiraling inward, are heated to millions of degrees, releasing radiation across the spectrum. These emissions allowed scientists to map the accretion process, the feeding frenzy that marked the last moments of matter before crossing the event horizon. But in those violent outbursts also lay clues: the behavior of particles, the shape of magnetic fields, the patterns of jets that extended thousands of light years. Each observation tested relativity, and each one, so far, confirmed it. Yet confirmation did not resolve the singularity. The deeper science looked, the stronger the contradiction became. Another frontier lay in time itself. Black holes slowed the passage of time through gravitational dilation. Atomic clocks orbiting Earth already confirmed this effect on a small scale. Near a black hole, it became cosmic. For the first time, relativity was not only a theory, but an experiment written across the stars. Light, escaping from near the event horizon, stretched, reddened, and weakened, precisely as Einstein had predicted. Yet these same observations raise the unspoken question: if time could slow to a halt at the horizon, what became of it beyond? Was time destroyed at the singularity, or transformed into something unimagined? Computational simulations became another tool. Supercomputers modeled the collapse of stars, the dynamics of merging black holes, and the evolution of accretion disks. These simulations pushed equations to their limits, revealing phenomena no telescope could yet capture. Some simulations hinted at exotic possibilities: echoes in gravitational waves, oscillations in accretion disks, and signatures that might distinguish black holes from gravastars. But predictions demanded confirmation, and confirmation remained out of reach. Meanwhile, gravitational wave astronomy expanded. Each new detection refined humanity's hearing of the cosmos. Black holes collided in pairs, trios, and in systems heavier than expected. Some signals hinted at intermediate mass black holes, bridging the gap between stellar remnants and supermassive giants. Yet the question remained: what exactly merged? If gravastars could mimic black holes, could the signals themselves be illusions? Scientists began searching for faint after-echoes in the waveforms, tiny ripples that might reveal a surface where theory predicted none. The searches continued, but the results remained inconclusive. On Earth, particle physics joined the investigation. Some theorists speculated that mini black holes might appear in high-energy collisions, such as those in the Large Hadron Collider. If such objects could form and evaporate instantly, they might reveal how gravity and quantum mechanics unite. No such detections had yet occurred, but the experiments underscored the unity of scales. From the subatomic to the galactic, black holes, or their alternatives, held the key to bridging physics. Perhaps the most haunting line of investigation was philosophical. As evidence mounted, physicists wrestled not only with what black holes were, but with what they meant. If singularities existed, then the universe contained points where knowledge failed. If gravastars or other exotic objects replaced them, then the cosmos might be protecting itself from infinity. Either way, black holes forced a reflection on the limits of science itself. The Event Horizon Telescope, after its success with M87, turned towards Sagittarius A star, the black hole at the heart of the Milky Way. In 2022, its image was unveiled, a faint ring of light surrounding darkness, smaller, closer, and more personal than the giant in Virgo. The image confirmed relativity once again, but also reignited the debate. Could such shadows be produced by structures other than black holes? Was the cosmos showing its face, or merely a mask? Deeper investigation thus reached a paradoxical stage. The more precisely black holes were studied, the more they confirmed relativity's predictions. Yet every confirmation reinforced the singularity problem, the information paradox, the clash between relativity and quantum mechanics. Gravastars, wormholes, fuzzballs, and other possibilities remained speculative, but each represented humanity's refusal to accept that infinities were the end of the story. In laboratories, in observatories, in the silent language of simulations, the investigation pressed on. Black holes were no longer abstractions, but the most scrutinized objects in the universe. And yet, behind every success lingered the same haunting truth. The horizon remained unbroken. Beyond it, observation ended and imagination began. The phase of discovery had shaken science. The phase of deeper investigation revealed something even more profound, that the closer humanity came to black holes, the further away their true nature receded. They were not just puzzles to solve, but mirrors reflecting the limits of knowledge, thresholds reminding humanity that the universe was more than equations, more than observation, more than understanding. They were mysteries designed not to be conquered, but to be endured, until new physics or new vision could pierce the darkness beyond the veil. By the dawn of the 21st century, black holes had shifted from mythic speculation to central pillars of astrophysics. Yet, the more closely they were observed, the more disturbing their nature became. Discovery had been a triumph. Investigation had been a relentless pursuit of evidence. But escalation was something else entirely. With each new observation, the mystery did not diminish. It deepened. It expanded. It reached into the heart of physics and threatened to unravel everything thought to be secure. The singularity remained the sharpest wound. Relativity demanded its existence. A place of infinite density, zero volume, and endless curvature of spacetime. But quantum mechanics refused to accept infinities. The contradiction between the two most successful theories of science could no longer be dismissed as a mathematical quirk. The deeper humanity looked, the clearer it became. Black holes were not just astronomical objects, but the battlefield upon which the greatest war in physics was being fought. The information paradox sharpened this conflict. Hawking radiation implied that black holes could evaporate. If so, what happened to the information contained within? Relativity said it was lost forever. Quantum mechanics said it could not be destroyed. The paradox was no longer an abstract debate. It was a fracture in the foundation of science. To allow one theory to triumph would be to shatter the other. And yet, both had been proven beyond doubt in their respective realms. Escalation meant that physics itself was at risk of collapse, unless a deeper framework could reconcile the irreconcilable. New observations only heightened the tension. Gravitational waves carried the sound of collisions between invisible giants. These signals were not vague hints, but precise measurements, confirming the predictions of relativity with astonishing fidelity. Black holes merged, space rippled, detectors on Earth trembled in response. And still, within the perfection of relativity's predictions, the singularity remained hidden. Confirmation became condemnation. The more accurate relativity proved, the more undeniable the paradox became. Meanwhile, theorists introduced ever stranger possibilities. Some argued for firewalls, violent walls of energy at the event horizon that would incinerate anything crossing over, breaking the smoothness of spacetime. Others proposed fuzzballs, where string theory replaced the singularity with tangled webs of fundamental strings, spreading matter into exotic configurations. Some whispered of gravastars, structures without singularities, hollow shells encasing dark energy-like cores. Each theory sought to avoid the horror of infinities. Each revealed how desperate science had become to escape the abyss. The escalation was not limited to theory. It was emotional, philosophical, and human. If black holes destroyed information, then the universe itself was not fully knowable. If they preserved it, then reality must function in ways no current equation could describe. Either outcome demanded a revolution in thought. Black holes were no longer silent cosmic predators. They were questions sharpened into objects, paradoxes made real. The Event Horizon Telescope's image of M87 star deepened the mystery. To many, it was proof. To others, it was a mask. Could a Gravastar cast the same shadow? Could a wormhole mimic the same ring of light? If two radically different objects produced the same observational signature, how could they ever be distinguished? Escalation meant that discovery had reached its limit. The universe itself seemed to conspire to hide the truth. The mystery also expanded to scale. Supermassive black holes, billions of times heavier than the Sun, seemed to exist in the earliest epochs of the universe, only a few 100 million years after the Big Bang. How could such titans form so quickly? Stars could not collapse into monsters of that size in so little time. Did they emerge from the collapse of primordial gas clouds? Were they seeded by exotic processes unknown to current physics? Or were they never black holes at all, but alternative structures, gravastars or boson stars, masquerading as singularities? The deeper the evidence ran, the more profound the questions became. Black holes were no longer isolated mysteries. They were cosmic keystones, shaping galaxies, influencing evolution, and anchoring the expansion of the universe itself. To misunderstand them was to misunderstand the cosmos. And yet, the more science tried to grasp them, the more elusive their essence became. This was escalation, not the growth of answers, but the multiplication of contradictions. Each triumph of observation deepened the wound in theory. Each new piece of data sharpened the paradox. The universe had revealed its darkest objects, and with them, its deepest refusal to be understood. The paradoxes of black holes did not remain confined to textbooks or abstract conferences. They grew louder with each scientific breakthrough, until the contradictions themselves began to drive the progress of physics. Escalation meant that black holes were no longer merely puzzles to be solved. They had become the stage on which the deepest drama of modern science was unfolding. The information paradox was the sharpest edge of this escalation. If black holes truly destroyed information, then quantum mechanics, the most successful theory of the microscopic world, would collapse. But if they preserved it, then relativity, the grand theory of spacetime, would need to be rewritten. There was no middle ground. Every attempt at reconciliation revealed the fragility of knowledge. Some proposed that information might be smeared across the event horizon itself, encoded holographically on the boundary. Others suggested that subtle correlations in Hawking radiation could carry the lost details back into the cosmos. But none of these solutions had yet been proven, and the paradox continued to burn like a wound in the fabric of science. Observations kept deepening the contradictions. Black holes that should not exist, too massive, too young, too perfectly aligned with theory, appeared across the universe. Some had spins approaching the maximum allowed by relativity. Others sat in the early universe, mere hundreds of millions of years after the Big Bang, where no known process could have built them so quickly. Their very existence mocked current theories of cosmic evolution. Escalation meant not only deeper paradoxes, but deeper challenges to the timeline of creation itself. Even the collisions recorded by LIGO and Virgo carried unsettling hints. In some signals, scientists searched for faint echoes, subtle ripples that might betray a surface rather than a horizon, a gravastar instead of a black hole. The instruments were not yet sensitive enough to decide, but the possibility lingered. Were physicists listening to the death cries of singularities, or to the collisions of hollow shells mimicking their shadows? Theorists pushed further into speculation. Firewalls, fuzzballs, wormholes, gravastars, each offered a way out of the paradox, but each carried costs. Firewalls shattered the smooth elegance of relativity. Fuzzballs demanded the machinery of string theory, itself untested. Gravastars required exotic states of matter that had never been observed. None provided certainty. Instead, they revealed how desperate science had become to escape infinities. The escalation was also existential. If black holes destroyed information, then history itself could vanish. The memories of stars, the structure of atoms, even the records of galaxies could be erased without a trace. Such a universe would be unstable, its future disconnected from its past. If, on the other hand, information was preserved in ways yet unknown, then reality itself might function like a cosmic code, indestructible and eternal. Either vision was profound. Both carried consequences for how humanity understood not only physics, but existence itself. Philosophers joined the debate, arguing that black holes represented the limits of knowledge. Some saw them as reminders that science was a human construct, inevitably broken by the vastness of the cosmos. Others believed they were invitations, challenges designed by nature to push human understanding into realms not yet imagined. In classrooms and observatories alike, black holes ceased to be distant objects. They became mirrors reflecting humanity's struggle with infinity. The Event Horizon Telescope's image of Sagittarius A star in 2022 only sharpened this escalation. Here, in the center of the Milky Way, humanity's own galaxy revealed the darkness at its heart. The glowing ring of plasma around the void was a confirmation of relativity, but also a silence. No image could ever reveal what lay beyond. The horizon remained intact, the mystery unbroken. Escalation meant that every advance was double-edged. Every proof of relativity reinforced the singularity problem. Every observation of horizons deepened the information paradox. Every confirmation of black holes intensified the possibility that they were not what they seemed. The closer humanity came, the more distant the truth became. And so the mystery did not shrink, it grew. Black holes were no longer isolated enigmas. They were global challenges to physics. Cosmic riddles that demanded revolutions of thought. The escalation of the black hole mystery was a reminder that the universe was not a solved puzzle, but a living question, always expanding, always deepening, always daring humanity to follow it further into the dark. The escalation of paradoxes surrounding black holes forced physicists to step into territory that was part science, part speculation. If singularities truly existed, then the universe contained infinities, something many scientists refuse to accept. If information were lost, then quantum mechanics would collapse. If it were preserved, then relativity would need rewriting. Theories and speculations became the lifeline of modern physics. an attempt to chart the unknown with maps drawn from mathematics, imagination, and fragments of evidence. The first and most direct path of speculation asked whether black holes were really black holes at all. Powell Mazur and Emil Motola proposed the Gravastar in 2001, a gravitational vacuum star. In their model, the collapse of a star does not lead to a singularity. Instead, spacetime transitions into a new state of energy, a kind of dark energy core surrounded by an ultra-dense shell. From the outside, a gravastar would mimic a black hole perfectly. Its gravitational pull, its horizon-like boundary, even the accretion processes around it could all appear identical. Yet inside, it would be radically different, hollow, stable, and free of infinities. This idea gained attention because it offered an escape from singularities and the information paradox. If no true horizon formed, then information might never be truly lost. It could be stored or reflected at the boundary of the gravastar. But gravastars required physics beyond current observation. The vacuum energy at their core was hypothetical, untested, and perhaps unreachable. Still, their very existence as a possibility revealed the desperation of science to avoid the abyss of infinity. Other speculations took different paths. String theory, with its vast landscape of extra dimensions and vibrating strings, proposed the fuzzball model. In this vision, black holes were not empty regions with singularities, but tangled masses of fundamental strings. The horizon was replaced with a surface of complexity, spreading the mass across a region rather than compressing it into a point. Fuzzballs could preserve information, storing it in their tangled structure. But string theory itself remained unproven, and fuzzballs remained mathematical constructs awaiting evidence. Another radical possibility emerged from the holographic principle. Inspired by black hole thermodynamics, this principle suggested that the information of a region of space might be stored on its boundary rather than within. If true, black holes could act like cosmic holograms, encoding the three-dimensional details of everything that entered them onto their two-dimensional horizons. In this way, information might never be lost. It would only be transformed. This principle extended far beyond black holes, suggesting that the entire universe itself might be a holographic projection of information stored on a distant boundary. Loop quantum gravity offered yet another speculation. Unlike string theory, it attempted to quantize space-time itself, breaking it into discrete loops of geometry. Within this framework, singularities might never form. Instead, collapsing stars could bounce, producing black hole-like objects without infinities. Some models even suggested that black holes might connect to white holes, objects where matter and information were expelled instead of absorbed. If true, every black hole could be a doorway, linking collapse to explosion, absorption to release. Wormholes, too, emerged as speculative cousins of black holes. While relativity allowed the mathematical existence of wormholes, tunnels connecting distant regions of spacetime, no evidence for them yet existed. Some theorists wondered if what appeared to be black holes might instead be wormholes, their horizons disguising tunnels to other universes. Such ideas bordered on science fiction, yet they were born directly from the equations of relativity itself. Each speculation came with a cost. Gravastars required exotic states of matter. Fuzzballs relied on untested string theory. Holography redefined the meaning of space and time. Loop quantum gravity demanded a new structure of spacetime. Wormholes required stability mechanisms that might not exist. But each offered something black holes could not: a way to escape the infinities that haunted science. Speculation was not weakness, it was a necessity. Physics had reached a boundary where data alone could not decide. The horizon of a black hole concealed the truth, and so theories multiplied in its shadow. The very act of speculation became a reflection of the mystery itself. The deeper the paradox, the more radical the imagination required to confront it. Speculation about black holes was never idle fantasy. It was the unavoidable response to paradoxes that refused to yield. Each theory stretched the imagination, but each also carried a fragment of plausibility, drawn from mathematics, experiments, or the whisper of evidence. Together, they painted a vision of the cosmos that was as unsettling as it was inspiring. One of the boldest ideas emerged from the firewall paradox. In 2012, physicists argued that the smoothness of spacetime at the event horizon might break. Instead of a gentle crossing, any object falling into a black hole might be incinerated by a searing wall of energy, a firewall. This proposal attempted to resolve the information paradox, but at a terrible cost. It violated the equivalence principle, one of Einstein's most cherished insights. The horizon, once thought to be invisible to the falling traveler, would instead become the most violent surface in the universe. Firewalls represented the willingness of physics to sacrifice even its most sacred principles in order to save information. Another avenue was the idea of black hole remnants. Some theorists propose that evaporation through Hawking radiation might not continue to completion. Instead, the process might leave behind a stable remnant, tiny, dense objects storing all the information that had fallen in. Such remnants would solve the paradox, but they came with their own challenges. If every black hole left one behind, the universe could be flooded with remnants, destabilizing cosmology itself. Still, the concept persisted as one of the more conservative attempts to preserve information without rewriting the foundations of physics. Speculation also turned toward the birth of black holes. If supermassive black holes existed so early in cosmic history, perhaps they were not born from stars at all. Some models suggested primordial black holes, objects formed in the chaotic density fluctuations of the infant universe. These ancient entities could have seeded galaxies, acted as dark matter, or survived as fossils of the Big Bang. Primordial black holes expanded the mystery beyond collapse, suggesting that black holes might be as old as time itself. More exotic still were theories linking black holes to the multiverse. If collapsing stars are connected to other regions of spacetime, black holes could serve as cosmic gateways. Some models of inflation suggested that every black hole might spawn a new universe inside, its singularity blossoming into a new Big Bang. In this speculative framework, our own universe could be the interior of a black hole formed in another cosmos. It was a vision that blurred the line between science and philosophy, but it grew naturally from attempts to reconcile singularities with creation itself. The holographic principle remained one of the most influential speculations. By treating horizons as surfaces encoding information, it offered a way to bridge relativity and quantum mechanics. It suggested that space and time were emergent, built from information itself. Black holes were not destroyers of knowledge, but guardians of it, their horizons recording every detail of what fell inside. This principle found surprising support in string theory and in the study of quantum entanglement, where patterns mirrored those of black hole thermodynamics. If true, the universe was not only a physical structure, but an informational one, where reality itself was a vast hologram. Even more radical was the idea that black holes might not be the end of stars at all, but transformations into new states of matter. Boson stars, supported by hypothetical particles called axions, could mimic the gravitational pull of black holes without singularities. Gravastars, already suggested, remained contenders, their shells and vacuum cores offering elegant solutions to infinities. Each alternative sought to show that what science called black holes might be masks for something stranger, objects not of collapse, but of metamorphosis. Theories multiplied, but none triumphed. Each was consistent in some ways, inconsistent in others. Each resolved certain paradoxes, but created new ones. In their diversity lay a profound truth. Black holes had forced physics into speculation not as a weakness, but as a method. To stand at the edge of the event horizon was to stand at the edge of certainty itself, where imagination became a tool of survival. For the public, these theories often sounded like science fiction. Firewalls, fuzzballs, wormholes, multiverses, they evoked the language of fantasy. But for physicists, they were serious attempts to grapple with contradictions that could not be ignored. Escaping singularities, preserving information, reconciling theories, these were not optional tasks, but urgent necessities. Without them, the edifice of science risked collapse. The deeper speculation went, the more profound the reflection became. If black holes were gravastars, then the universe was self-regulating, avoiding infinities. If they were fuzzballs, then matter itself dissolved into strings, rewriting the meaning of substance. If horizons were holograms, then space and time were illusions, projections of information. Each theory not only redefined black holes, but redefined reality. Speculation, then, was not the opposite of truth. It was the bridge between paradox and understanding. It was the willingness of science to admit its limits and to dream beyond them. Black holes had forced physicists into this posture, turning equations into poetry, paradoxes into possibility. Theories and speculations had become the language of survival at the edge of knowledge, each one a flicker of light against the infinite darkness of the event horizon. The mysteries of black holes could not be resolved by speculation alone. To distinguish between singularities and alternatives, such as gravastars, science required tools, instruments capable of probing the very limits of nature. These tools were not simple telescopes gazing into the night sky, but vast collaborations, networks stretching across continents, detectors buried beneath mountains, and satellites orbiting far above the Earth. In the 21st century, the investigation of black holes became a global enterprise, each instrument designed to press closer to the horizon and test the paradoxes born from theory. The Event Horizon Telescope, EHT, was the most iconic of these efforts. By linking radio observatories around the globe through very long baseline interferometry, it transformed Earth itself into a single telescope the size of a planet. Its achievement in 2019, capturing the first direct image of the shadow of a black hole, M87 star, was more than a triumph of technology. It was the confirmation that relativity's predictions of a glowing ring surrounding a central darkness were accurate. In 2022, the EHT delivered a second historic image, this time of Sagittarius A star, the supermassive black hole at the center of the Milky Way. Each success brought humanity closer to the horizon, though never across it. Meanwhile, gravitational wave astronomy opened a new window into the cosmos. LIGO in the United States and Virgo in Italy detected space-time ripples from colliding black holes, confirming Einstein's century-old predictions. These detections were not only confirmations of relativity, but also opportunities to search for subtle deviations. Some theorists predicted that if gravastars or other exotic objects merged, the resulting waves would carry faint echoes, patterns hidden in the signal that could betray their true nature. Thus far, no clear anomalies had been confirmed, but the search continued with growing sensitivity. Future instruments like LISA, a space-based interferometer planned for the 2030s, promise to extend these capabilities, listening to the deepest rumbles of the universe with unprecedented precision. X-ray and gamma-ray telescopes added another dimension. The Chandra X-ray Observatory and NASA's NuSTAR mapped the high-energy emissions from gas spiraling into black holes. These instruments revealed the dynamics of accretion disks, jets, and hotspots orbiting dangerously close to horizons. By studying these patterns, scientists tested relativity under conditions impossible to reproduce on Earth. The behavior of matter in such extreme environments could, in theory, reveal differences between black holes and gravastars, though so far, the data continued to mirror Einstein's equations with eerie perfection. Even pulsars became tools. These rapidly spinning neutron stars emitted precise radio pulses, acting like cosmic clocks. When a pulsar orbited near a black hole, the timing of its pulses could be distorted by spacetime itself, offering yet another way to test gravity. Astronomers searched for such systems, hoping that pulsar timing could reveal the subtle fingerprints of horizons or alternatives. On Earth, supercomputers served as instruments in their own right. Simulations of black hole mergers, accretion disks, and relativistic jets allowed physicists to predict what instruments should detect. These models grew in complexity, integrating relativity, magnetohydrodynamics, and quantum effects. They provided the templates used to analyze gravitational wave signals and interpret EHT images. In the absence of direct access beyond the horizon, simulations became windows into the inaccessible. Particle physics also joined the search. Some theorists speculated that miniature black holes might appear in high-energy collisions, such as those at the Large Hadron Collider. Their appearance would reveal how gravity behaved at quantum scales, perhaps even offering clues about unification with other forces. Though no such mini black holes had yet been detected, the mere possibility linked the smallest scales of matter with the largest scales of the cosmos. The deeper science reached, the more collaborative it became. Thousands of researchers, dozens of institutions, and entire nations contributed to the study of black holes. Each tool, whether a telescope, detector, or computer, was part of a larger network, humanity itself becoming the instrument to probe the abyss. And yet, for all the triumphs, the horizon remained sealed. No instrument, however advanced, could pierce it. The event horizon was not just a boundary in space, but a limit of knowledge, a line where data ended and speculation began. Still, science pressed forward, driven not only by curiosity, but by necessity. If black holes were truly singularities, then physics as it stood was incomplete. If they were gravastars or other exotic structures, then discovery would demand rewriting the story of the universe. In either case, the tools of investigation were the only way to decide. Each signal, each image, each ripple in spacetime was a fragment of truth pulled back from the edge of the impossible. If the Event Horizon Telescope and gravitational wave detectors represented the eyes and ears of humanity, then the future promised senses even more profound. The challenge of black holes demanded instruments not only larger, but more sensitive, capable of detecting the faintest ripples in spacetime and the weakest echoes of radiation. Each new tool brought with it the hope of peeling back a layer of the unknown, of distinguishing whether black holes were truly singularities or if gravastars and other exotic alternatives hid in their disguise. The Laser Interferometer Space Antenna, LISA, scheduled for the 2030s, symbolized the next leap forward. Unlike ground-based detectors limited by Earth's vibrations, LISA would orbit in space, its arms millions of kilometers long. It would listen to gravitational waves from sources too massive or too distant for current instruments, mergers of supermassive black holes, signals from the early universe, and perhaps even the faint aftershocks of primordial black holes. If exotic objects such as gravastars existed, their collisions could leave subtle imprints in these signals, differences in the ringdowns or echoes after the merger. LISA's mission was not only to confirm relativity, but to challenge it, to strain the theory against the universe's heaviest objects. Other projects, such as pulsar timing arrays, used the universe itself as an instrument. By monitoring the precise rhythms of pulsars across the galaxy, astronomers search for the telltale distortions of passing gravitational waves. In 2023, these arrays announced the first hints of a cosmic gravitational wave background, a low hum echoing across the universe. If confirmed, this background could reveal the growth of black holes across cosmic history, mapping their mergers on scales far beyond individual detections. High-energy astronomy, too, continued to refine its gaze. Instruments like the European Space Agency's Athena mission, planned for the late 2030s, promised to probe the X-ray skies with sharper clarity than ever before. By studying the accretion disks and relativistic jets around black holes, Athena might detect anomalies invisible to current telescopes. Were horizons truly smooth, or could subtle irregularities betray the presence of surfaces? Could the light curves of orbiting hotspots distinguish between black holes and gravastars? These questions turned future observatories into weapons against paradox. Even cosmic neutrinos, ghostly particles that rarely interact with matter, became tools of exploration. Detectors like IceCube, buried deep in Antarctic ice, traced neutrinos from violent cosmic events. Some of these neutrinos seemed to emerge from the environments of black holes, carrying information unaffected by magnetic fields or scattering. If neutrinos could be tied directly to horizons, they might offer clues hidden from photons and gravitational waves alike. On Earth, the synergy between theory and observation continued to grow. Supercomputers modeled not only black hole mergers, but also exotic alternatives, predicting the faintest distinctions between them. Teams of physicists scoured gravitational wave data for hints of echoes or irregularities, searching for cracks in relativity's armor. Although none had yet been found, the very act of looking demonstrated how science had evolved. No longer content to confirm relativity, it now sought its limits. The pursuit of tools was also a pursuit of unification. The paradoxes of black holes represented the conflict between relativity and quantum mechanics. Instruments capable of probing horizons, ringdowns, and radiation were, in effect, instruments designed to bridge the two great frameworks of modern science. Every new telescope, every detector, every simulation was not only a study of the cosmos, but a step toward a new physics. And yet, for all the power of these tools, the mystery persisted. The event horizon remained opaque, the singularity forever hidden. Instruments could trace the motions of stars, the ripples of space, the glow of plasma, but none could cross the veil. The truth of black holes, or gravastars, remained sealed. forcing science into a delicate balance, to press further, to build larger, to listen more carefully, and to admit that perhaps some truths would forever be beyond reach. But science was not deterred. It had never been deterred. From Michel's ink to Einstein's equations, from Schwarzschild's battlefield solution to Hawking's paradox, black holes had always represented the edge of possibility. The tools of the 21st century were not the end of this pursuit, but the beginning. They were humanity's hands reaching toward the abyss, straining to touch what could not be seen, what might not even exist as imagined. Whether they revealed singularities or gravastars, whether they confirmed relativity or shattered it, the tools themselves carried a promise that humanity would continue to search, even at the edge of knowledge, even at the brink of infinity. The journey into black holes, or gravastars, had not only been a scientific expedition, it had also been a journey into philosophy, into the meaning of knowledge itself. By the time humanity stood at the edge of the event horizon, the questions had grown larger than equations. They had become mirrors, reflecting the fragility of certainty, the mystery of existence, and the humility required to confront the cosmos. At the heart of this reflection was the singularity. If infinities truly existed, then the universe contained places where reason failed, where prediction collapsed, where knowledge ended. For some, this was a tragedy, a reminder that science, for all its triumphs, could not conquer reality in its entirety. For others, it was a revelation that mystery was not weakness, but strength, a sign that the cosmos was deeper than imagination, broader than intellect, richer than comprehension. Singularities, real or not, forced humanity to admit that its language of mathematics and experiment might always encounter limits. Gravastars, in turn, carried their own philosophical weight. If such objects existed, if the universe refused infinities by substituting balance for collapse, then reality was not only intelligible, but merciful. The cosmos in this vision was not a destroyer, but a preserver, avoiding the catastrophic end of knowledge by rewriting its rules at the edge of extremes. Gravastars would not only resolve paradoxes, they would reshape philosophy, suggesting that nature carried within it a principle of protection, a refusal to allow knowledge to vanish into nothingness. These reflections touched not only physics, but the human spirit. For centuries, the night sky had been a canvas for meaning. Constellations mapped into myths, comets feared as omens, planets tied to gods. Black holes had shattered that tradition, replacing visible symbols with invisible abysses. To gaze at a galaxy's core was to know that behind its light lay darkness, and behind that darkness, mystery. Humanity's cosmic myths had been replaced by equations, but the awe remained as deep and haunting as ever. The paradoxes of information loss extended beyond science into existential reflection. If black holes destroyed information, then history itself was fragile. Every memory, every structure, every trace of being could be erased without return. Such a universe was one of impermanence, where the past could vanish into silence. If, however, information was preserved, then reality carried a hidden permanence, a cosmic memory embedded in horizons, a guarantee that nothing was ever truly lost. Both visions carried weight. Both reshaped how humanity might see itself, either as fleeting sparks in a forgetful cosmos, or as indelible patterns in a universe that remembers. The tools of science revealed more than data. They revealed the character of the quest itself. To build instruments spanning the globe, to detect ripples smaller than an atom, to peer across billions of light years. This was not only an act of discovery, but of devotion. Humanity had become a species defined by its refusal to accept the horizon as an end. Even when answers remained hidden, the act of searching became its own philosophy, its own form of meaning. In quiet moments, scientists themselves confessed to wonder. Equations could predict orbits, simulations could model jets, detectors could record waves, but none could erase the feeling of standing at the edge of the unthinkable. To imagine a singularity was to imagine the death of knowledge. To imagine a Gravastar was to imagine the possibility of redemption. To imagine either was to admit that the universe was not only physical, but poetic, a story told in both numbers and silence. Philosophy asked questions science could not. What does it mean to live in a universe with horizons? What does it mean to know that some truths may never be known? What does it mean to confront infinities or their absence? Black holes and gravastars were no longer only about stars and gravity. They were about existence itself. What it means, what it forgets, what it remembers. And so the reflection deepened. The cosmos had given humanity riddles, not solutions. Black holes revealed paradox. Gravastars offered alternatives, but neither dissolved the mystery. Instead, they magnified it, leaving humanity not with finality, but with wonder. Perhaps that was the truest gift of the abyss. Not answers, but questions eternal enough to outlast even stars. If black holes had begun as mathematical curiosities and gravastars as speculative rescues, their true legacy was philosophical. They had forced humanity to confront the most difficult question of all. What are the limits of understanding? In the cold vacuum of space, hidden behind horizons, lay challenges not only to physics, but to meaning itself. One path of reflection considered time. At the event horizon, time slowed to a crawl for the distant observer. Within, it raced toward collapse. Was time destroyed at the singularity, or reborn as something unknown? If gravastars existed, did they preserve time in strange new forms, balancing collapse with expansion? These questions reshaped the philosophy of temporality, suggesting that time itself might be local, fragile, and contingent. The cosmos was no longer an eternal clockwork, but a patchwork of perspectives, stitched together by relativity and fractured by horizons. Another reflection turned to identity. If information was lost in black holes, then the universe did not preserve the uniqueness of being. Histories could vanish, individuality could dissolve into silence. But if information was preserved, whether in holographic horizons, fuzzball tangles, or gravastar shells, then the universe was a vast archive, remembering every pattern, every choice, every life. In this vision, identity was not ephemeral, it was cosmic. Humanity itself became part of an eternal record, inscribed in the very fabric of spacetime. Ethics, too, found a shadow in the abyss. If knowledge itself had limits, then humility became a virtue. The pursuit of black holes demanded not only intelligence, but restraint, an acknowledgement that certainty may forever remain beyond reach. To embrace mystery was to embrace responsibility, to seek, but not to claim absolute possession of truth. Black holes, in this way, became ethical teachers, reminding humanity that arrogance collapses as surely as stars. The reflection extended to existence itself. Black holes suggested a universe that devoured, that destroyed, that ended. Gravastars suggested a universe that protected, that balanced, that transformed. Between them lay two visions of reality, one tragic, one redemptive. Yet both carried beauty. The abyss was not simply horror, it was grandeur. It revealed that even destruction was part of creation, even silence part of music, even darkness part of light. For scientists, these reflections were not mere philosophy. They were the atmosphere of discovery, the emotional weight that accompanied every equation. To spend a life studying horizons was to live in dialogue with the infinite, to simulate collapses, to detect waves, to image shadows. These acts were not only technical, but spiritual, drawing humanity into a confrontation with what it could not fully grasp. In the end, the close of the journey was not resolution, but reverence. Black holes and gravastars had not answered the final question of what lay beyond the event horizon. They had sharpened the mystery, magnified the paradox, and deepened the awe. Perhaps that was the only answer the cosmos intended to give. To stand at the edge of the horizon was to stand at the edge of knowledge, where science and philosophy touched, where certainty dissolved into wonder. And so the narrative ended not with closure, but with invitation. The universe remained unfinished, its truths still veiled, its horizons still intact. But in the persistence of questioning, in the courage to search, in the humility to accept mystery, humanity found its place, not as conquerors of knowledge, but as companions of the unknown. The abyss did not end the story. It carried it forward into future tools, future theories, future reflections. Whether the cosmos held black holes or gravastars, infinities or balances, erasures or archives, the meaning was the same. The search itself was the answer. The event horizon was not only a boundary in space, it was a symbol of the edge of understanding, of the endurance of wonder, of the eternal dialogue between humanity and the stars.